Okay, so what I'll be talking about today is jet formation and transport in baroclinic turbulence with simple topography. So let's just start with a bit of an introduction. I think everyone in the room here will be familiar that the ocean and atmosphere are filled with coherent structures, whether they be atmospheric storms, ocean eddies, or what we'll focus on today is jets, and that these structures play a key role in transport processes. Now, because these structures are typically on the scale of or smaller than the grid scale of large ocean circulation or climate models, their effects generally need to be parameterized. Now, one region of the ocean where this is especially true is the Antarctic circumpolar current. Peter's mentioned this, and I'm just showing it schematically here in red. And it's a unique current because in the latitudes across Drake Passage here, there are no continental boundaries, and so you have a circumpolar flow. Now, because you have a circumpolar flow, this current acts a lot like an atmospheric flow, and so different from circulation in ocean basins, you get much larger zonal mean flows developing, you have a greater sensitivity to topography, and perhaps most importantly, eddy processes really dominate meridional transport. Okay? And you can see the role here that the ACC may potentially play as a barrier to transport between properties, be it heat, chemicals, tracers, moving north and south. Okay? And so one of the challenges in modeling transport in the ACC is that there is a lack of consensus in the literature really about what the important length scales are for transport in this region. And so to kind of summarize that, I've got three views here of the ACC from three different studies. And so the first view here is from a recent study by John Marshall and his colleagues, where they've taken surface velocities in the ACC, used it to evict tracers, and from that backed out eddy diffusivities. And so what these colors are showing are magnitudes of eddy diffusivities. And so you see this big band of blue all the way around Antarctica. So in this view, the ACC is acting as a single large-scale barrier to meridional transport. Now, this is somewhat different from the traditional view. This is a picture from Orsi's paper in 1995, where the ACC is typically described as having three coherent circumpolar fronts that can be traced right around the continent. And so this really comes more from a hydrographic viewpoint, whereby you pick, for example, a particular isotherm, find its most northern extent at a certain depth, and it's very easy to trace that property all the way around the continent. What's less clear is how well that definition actually traces where the high gradient properties are, which is what you'd normally associate with fronts.
It's not a fat barrier. That's a rather fat barrier. You think?
It is a rather fat barrier, and that's the point. This is one single large-scale barrier. This is giving you three fronts. And in the most recent view, which has really come out of eddy resolving simulations, and also from satellite altimetry, is what I'm showing here. This is a snapshot from the Occam 12th of the degree model. What the colors are showing are the magnitude of surface velocities. And what you can see from here is it's very difficult to pick out individual circumpolar structures. What you see is this very intricate web of small-scale jets. Okay, and so that's a numerical simulation, but you get similar pictures from observations as well. And so these are two figures from a nice paper by Sokolov and Rintoul. And what's being shown here is gradients in sea surface height. So this is taken from satellite altimetry, and the gradients in sea surface height are essentially a proxy for the magnitude of the surface velocities. Okay, and you can look at two pictures. This here is a snapshot. So you have longitude and latitude. This is Tasmania, south of Southern Island of New Zealand. And so as you pick a particular longitude here and move north, you don't cross three coherent jets. Okay, at any particular longitude, you may cross anywhere between 6 to 10 very narrow, fairly filamentary structured jets. And you can also see that these aren't zonal structures. There's quite a large deal of meandering going on here. If instead you pick a particular longitude, so in this case, if you stay at 140 degrees east and look at the temporal variability, that's what I'm showing here. So you take one slice, and you've got time going along the x-axis, this is 3 years. This is latitude here. Again, you still see those coherent structures coming out. You have these jets. And to a certain extent, they appear in the same location. That's largely due to topography. But as you take a closer look, you see lots of events here where these jets come together and they merge. You have regions here where you don't have much velocity, and all of a sudden you have a jet spontaneously forming. You may have a case here, you have a very strong jet, and all of a sudden you have a rapid shift in latitude. Okay? And so when you look at these sorts of pictures, the question comes, are there really circumpolar barriers to transport? And what does that mean in terms of large-scale mixing? Okay, so these are the types of questions I want to look at today, and I'm actually going to address this in a much simpler model. Okay, so what I'll be using actually is just a two-layer Phillips model that's baroclinically unstable, and I'm going to introduce some topography. So I'm going to do this in the presence of a large-scale potential vorticity gradient. So we'll do it on a beta plane and also with some topography. And very simply, the reason for using such a simple model is we want to explore a range of parameter space. Okay, so the model is kind of summarized in this diagram. Most people here will be familiar with it. What we're going to do is use a doubly periodic simulation. It's large compared with the deformation radius, so a large number of jets will form in the domain, similar to the Southern Ocean. We force the upper layer with a mean flow that gives you a baroclinically unstable tilt between the upper and lower layers, and that's the forcing of the system. Okay, and then we'll let this run and let it come into statistical equilibrium because we have some dissipation in here due to bottom friction. Okay, so these are just the evolution equations of the perturbation PV. You have some linear terms here, which is the large-scale potential vorticity gradient in the upper and lower layers. This is the forcing of the mean flow in the upper layer. Again, this is dissipation. Definitions are, as they usually are, stream function, potential vorticity, and deformation radius. And these are the definitions over here. Bottom friction has units of 1 on time, and it's a spin down time. And again, this H here is our topography, because as units of 1 on time, this is the definition. Okay, a couple interesting points to note. Beta here is the large-scale potential vorticity gradient. Because of the shear, you can see the upper layer actually shallows because of this unstable gradient. So shear actually enhances the PV gradient in the upper layer. And for the same reason, this lower layer deepens. It opposes beta in the lower layer. Okay, so these are the topographies I'm actually going to look at. They're very, very simple. What I've got here is a set of zonally invariant ridges. So you've got humps and troughs that vary in the meridional direction. And so we'll look at that case first. All this simply does is it modifies locally the large-scale potential vorticity gradients. And then we'll move to a slightly more complex case here. We have a series of sinusoidal bumps both in the zonal and the meridional direction. Note that these domains are much larger than the deformation radius. So this is roughly 60 deformation radii per side. So we'll get a large number of jets forming in this domain. Okay, and the parameters are going to vary, very simple. It's just the length scale of topography. Simplest way to describe that are the number of bumps, MB, or the number of ridges you have in your domain. L is the domain scale. LT is just the wavelength of your topography. And then the other thing is the topographical steepness. Okay? And so it's not just the amplitude of the topography we're looking at, but it's actually the steepness. So it's the maximum value of dH dy in this case. Okay, and so I just have one simple plot here, so there's a little bit of a busy plot, but I just wanted to give an idea of what example topography is doing to the, in this case, barotropic PV gradient. Okay, so the surface I'm showing here is just barotropic PV. This is the zonal and meridional directions in the case with sinusoidal bumps. And so the surface, you can see, is dominated by the large-scale linear gradient. And topography just acts to locally modify that gradient. Okay, and the colors here are just showing the gradient of the barotropic PV squared. So it's just where you see warm colors here, it's where the x and y gradients of PV are large. Okay, so the PV gradient is dominated by the linear gradient and is locally modified. Okay, so before I get to some results, I'm going to be using two diagnostics, so I'll just explain them relatively quickly. The first is the Rhine scale, and we're going to define that as is done in Panetta. So it comes from a velocity scale and beta. Take the square root of that, you get a length. And as Panetta showed in 1993, if you use an eddy velocity scale, then you end up getting a very good agreement between this length scale L beta with the jet width. And so then I'm going to define that as Lj, which is very simply just looking at the physical fields, counting the number of jets you have in the domain, and dividing it by the size of the domain. Okay? And so what I'm just showing here is looking at a number of simulations in the case where you just have a flat bottom. Okay, and this is taken from an earlier study that I looked at where we varied the bottom friction here along the x-axis and the strength of beta here along the y-axis. And what we've done is just contoured the number of jets you have in the domain to L beta here. And what you find is that over most of this domain, this is roughly 1. Okay? So the point really is that L beta is really measuring the meridional extent over which potential vorticity wants to mix. So you have this turbulence in a large domain, you set up a number of jets, and L beta is measuring the width over which that mixing occurs. Okay, and so we'll come back to that in a minute. The other diagnostic I like to look at is the effective diffusivity. Okay, and I've defined the effective diffusivity here. It's just a constant K times the ratio of two squared length scales. And so I'll just explain what those length scales are. If you have your domain, let's say it's just a square domain here, and you have a large scale gradient and a tracer field, and you can see you would get a number of tracer contours that just move across the domain. So this would be a high value of tracer and a low value of tracer. And you have a certain length associated with that tracer contour across the domain. You start up a simulation, you generate some eddies, you get some turbulence, and those eddies act to stretch that tracer contour. At some point that comes into equilibrium, and you have some equilibrated length of this contour. Okay, the point now is if you have a jet here, this stretches the contour somewhat, but it doesn't nearly do so as much as in a mixing region where you'd have much, much longer stretching with the contour. Okay, so the fact is that jets are associated with minimal tracer complexity. Okay, so we have short contours, you have low mixing, and you have low values of effective diffusivity. Where you have strong mixing, you have long contour lengths, you'd have a long length through here, and you have large mixing. Okay, so effective diffusivity is essentially a measure of tracer complexity, and I'm going to use it as a measure of transport in these simulations. Okay, and what I will be showing in the results here is the effective diffusivity diagnosed from upper layer potential vorticity, which is materially conserved. Okay, and so really just to cement this, I thought I'd give one example of what happens turbulence in a flat bottom case. Okay, so in a large domain with no bottom topography, we're looking at a simulation here where you have 4 strong eastward jets. Okay, now what's interesting is you actually see 8 bands here. So you'd see 1, 2, 3, 4, 5, 6, 7, 8 bands of strong mixing, and similarly 4 bands where it's very dark where you have low mixing. And so I've labeled here where the eastward jets are, 1, 2, 3, 4. And so what's quite interesting is that this is well understood, that you have low mixing where these eastward jets are. These are acting as barriers to transport. You have strong mixing on the flanks of the jets, but you're also getting some weaker barriers to transport here in the westward jets. And this supports some of the recent work that's been done by Bruno Vera and his colleagues. Okay, and so what this is these jets are evolving in time. This is meridian position, and so these are very, very steady jets that are forming. I'm going to look at what happens when we introduce some topography to this case. Okay, and then the last point to mention is that we'll be looking at some domain average statistics. So what we will do is just take this effective diffusivity and produce this curly bracket mean over it, which is simply the harmonic mean, which is typically what is used when looking at transport properties. Okay, so what I'm showing here now is a series of, again, this is time and position, so Hofmorler plots of this effective diffusivity for the cases where we've introduced some zonal ridges now. Okay, so this is the reference case I've showed before with a flat bottom with these parameters for beta and bottom friction. And what we're going to introduce now is some zonal topography, some zonal ridges. Okay, so that's the flat bottom case. If we introduce in this case 3 zonal ridges with a moderate ridge steepness, you can see that you get this very intricate braided structure now. So you still have many zonal jets across the domain, but now they're no longer steady and they're migrating great distance in the meridional direction.
But also the westward ones are fuzzier than the eastward ones, aren't they?
That's
in the middle of the picture.
In here.
That fuzzy black bit is a westward flow, I presume.
This part here.
Well, right in the middle where you pointed before. Sort of
Right through here.
Yeah, that one, yeah. That's a good example, isn't it?
That's right. That's right. Well, it's a bit difficult to see here, but to a certain extent, the westward barriers are also weaker barriers to transport.
Because you get the purely kinematic barrier effect, as in Baron-Verrat's work, when you're wavy, but the more strongly turbulent you are, the more robust the eastward ones are going to be, and the more fuzzy the westward.
That's correct. That's correct.
That's a nice demonstration.
That's right.
But actually, do you think that's really, could you really tell from those pictures that the eastward and the westward jets have different strength barriers?
Well, from this snapshot, you might have a difficult chance looking at it, but I mean, if you look closely at the values, I mean, essentially each of these is a profile that you put together to make this time evolution plot, and so you can go in and look at, individual profiles and quantify how strong those westward barriers are. Okay, so this is the case with 3 zonal ridges. If you then move up to 5 zonal ridges, what you find is that the jet structure is locking back into a very steady configuration. However, what happens in this case is that the number of jets you have here is different from what you have in the flat bottom case. they're actually narrower, and so you have 5 jets in this case compared to 4. If you introduce more ridges in this case, you're up to 8 ridges here, you revert back to the flat bottom structure. And finally, if you have 3 zonal ridges with a steeper topography, you can get this mixed, both braided and steady structure, whereby you have very strong jets that are forced by topography, and in between the two, you have a braided structure. Now, to kind of understand what these transitions are, the kind of key diagnostic to look at is this ratio LB on LT, where again, this is the meridional extent of PV mixing compared to the topographical wavelength. And so, I mean, some of this is quite clear. If this ratio is much larger than 1, that simply means that the eddies are mixing over your ridges. It doesn't feel the topographical scale, and so you revert back to this bottom structure. You can see this ratio here is 1.67. If the ratio is the same, so L beta is the same as the topographical scale, then you have very steady jets. The important point being that the topography can set the scale. So you can get this sort of steady structure for 5, 6, or 7 jets. And then finally, as the meridional extent of the PV mixing gets smaller than the topographical scale, you start to feel the local modifications to PV, and that's where you start to get this braided structure. And again, when you move down to very small ratios here, that's where you begin to get this mixed and steady behavior. So qualitatively, it's kind of easy to understand what's going on here. As you introduce topography, you've got regions where the topography enhances the PV gradient, enhances beta, and regions where it acts to impose the PV gradient. So you get regions of high PV and low PV. Where the PV gradient is low, you generate very large eddies, and you want to mix over a quite large region. So this is that long L beta scale here, whereas in regions where you have strong PV gradients, that scale is much weaker. And so what happens is you generate eddies that give you a large homogenized region here. This side of the ridge wants to actually form new jets. Once those jets form, it's no longer compatible with this large mixing region, and they need to do something to alleviate that. They need to come together and merge. What's a bit more interesting is actually looking at the mechanics of how that works. And so if you look at what happens, what forces rather the zonal mean energy, there's really 3 things that do that. The first is that you have a correlation between Reynolds stresses in the upper and lower layer. And this is the very familiar idea that you have correlation between the Reynolds stresses that takes energy out of the eddies and puts it into the mean flow. It's an upgraded momentum flux that people talk about with jets. And so that can happen in the upper and lower layer. And then this is just the baroclinic instability process. You take energy out of the mean flow and put it into eddies. So that's a sink. And then, of course, you have some bottom friction here. Now, if you look at just this term that I've labeled in black here, so the upper layer Reynolds stresses, and you look at it in the case with steady jets, the jet itself is in this dotted line here, and the Reynolds stresses are the solid line. And what you see is that it's symmetric about the jet, and it's positive on the jet flanks. And so what that means is the eddies on the jet flanks where the mixing is large is being converted into zonal mean kinetic energy and forcing those zonal jets. If instead you look at the case where you have this jet meandering, so in this braided structure, and you now show meridional position versus time, I'm showing the same term right here. And what you find is when you have these jets, it's no longer symmetric about the jets. Because of the local modifications because of PV, it's positive on one flank of the jet, negative on the other. And these Reynolds stress terms are in fact steering these eddies across latitudes here. They're steering these jets meridionally in order to maintain this balance between the topographical scale and the PV mixing scale. Okay, so then just a summary of some of the domain average statistics. This is just a summary of the simulations that have been run. This is along X, increasing number of ridges, and along Y, the ridge steepness. And then what I'm showing here are different estimates of transport. So there's the eddy heat flux, and this is that domain average effective diffusivity I was talking about. The details of this aren't important, but I just want to concentrate on 2 slices. So if we take a fixed steepness and increase the ridge number, what I'm showing here are these transport estimates, but now I'm showing a ratio to what you get in flat bottom values. Okay, so the first point here is that ratio is always less than 1. So when you introduce topography, you always get smaller transport, domain average transport estimates. And the other point is that you can see this plot has a number of local minima. Okay, it's non-monotonic behavior. And what's happening is as this simulation locks into different jet configurations, you get different values of the domain average transport. Okay, the trend is more clear if you keep the number of ridges fixed and increase the ridge steepness. In that case, you just get a monotonic decrease in domain average transport. And now that's actually quite interesting because as you introduce these ridges, you've got flanks of the ridge where you increase the PV gradient and flanks where you oppose it. And so this plot is telling you it's actually the regions where you enhance the PV gradient that are controlling the domain average mixing. The regions with that PV gradient become stronger.
Any heat flux equals form stress.
That's correct. Yeah. Okay, and so you can do a similar sort of thing with bumpy topography. I'm not going to spend much time on this. Again, this is the flat bottom case. You can get the same sort of braided structure. You can get the same number of steady jets when L beta on LT is close to 1. Note that in this case you actually have wider jets. So you have a fewer, the jet spacing is larger than in the flat bottom case. And then if that ratio is large, you revert back to the flat bottom structure. The one interesting thing is you do get some new behavior here when you introduce bumps. And so you can see these little black dots in here. Each of these are very strong barriers to transport, but they're transient. Okay, and so they form and then they disappear. And the other thing that you can see is that they're actually jumping throughout the domain here. So you get this very odd behavior that we'll look at in a minute. And I'm just going to show the same domain average statistics for the bumpy case. So now this is the number of bumps along the x-axis. This is the bump steepness along the y-axis. And once again, we're just going to take some slices through the data. So keep the steepness fixed and increase the number of bumps. And what you see here, again, this is a ratio to flat bottom values. And what you see now is that these values are all greater than 1. And not only that, this is actually a logarithmic axis. You have much larger variability here when you put bumps in your domain. And so if you keep the steepness fixed, you actually have a peak at some some intermediate value of bumps, which depends on the steepness. If you keep the bumps fixed and increase the steepness, you see you have two different regimes here. A weak transport regime that transitions very rapidly to a strong transport regime. And the transition occurs here when your steepness is strong enough to locally reduce your barotropic PV gradients to 0. Okay, so I just got a couple minutes. So I just wanted to show two examples from the bumpy topography case. So this is where you get the braided structure. Again, this is effective diffusivity as a function of time and position. Remember, white is strong mixing, and these dark regions are transport barriers. And what I've plotted here is just a time series of the kinetic energy in black and the effective diffusivity averaged over the domain as the dotted curve. And what you see is you have these quasi-periodic bursts in kinetic energy and mixing. And if you look at the Hofmorler plot, you can see that those are associated with major jet merger events. So as these jets come together, you get these bursts in transport. You can see there really aren't any other significant merger events in this plot.
And those are eastward jets.
So the very dark curves here are eastward jets, that's right. Yep. And so you can look at this example more closely in a somewhat more exaggerated version. And so now we've had 3 bumps in this case and a slightly steeper bump topography. And what you see is this very interesting, very periodic structure. And what I'm plotting here is kinetic energy in red, potential energy in dark blue, and zonal kinetic energy in light blue. And this is time. Sorry, that should not be positioned. It's just these values here. And so the interesting thing is you have this very periodic structure, but the potential energy is leading the kinetic energy, which is leading the zonal kinetic energy. All 3 are out of phase. And so what happens is when the kinetic energy is very weak, then the eddy length scales are small enough to feel the length scale of topography. And so you get topographical steering, which gives you a non-zonal mean flow, which is very efficient at extracting energy through baroclinic instability, and you get these big bursts in kinetic energy. As you get these big bursts, the eddy length scales grow and mix over the scale of the topography. And so you can see these are showing where the jets are here, where you have these red lines. And so you see you get these very transient jets, these very strong barriers to transport that are jumping throughout the domain. And so the best way to show what's going on here is to just show a movie. And so we start out in the high kinetic energy state, and you have very large eddies, which are mixing over the scale of the topography. And because it only feels the large-scale potential vorticity gradient, everything becomes very zonal. Okay? When everything becomes zonal, the energy decays, which we'll see in a minute in this state. And as that energy decays, the eddy length scales get smaller, they begin to feel the topography, and you can see this steering beginning. As you get non-zonal mean flows, you extract more energy, you get a big burst in kinetic energy here, and then you move to a state where it just feels the large-scale PV gradient. And it's bumpy topography. And so I'm sorry, I actually had these movies synced at one point. They didn't really agree with that. And I just want to show this red curve here, again, is the time series of domain average effective diffusivity. And again, when you have these high energy states, you have these strong bursts in mixing and transport. And this is that ratio L beta on LT. And you can see that in that weak state, this ratio just approaches 1. So you just start to feel the topographical length scales when you get some steering, and you get a big spike in the energy here. Okay? So to just summarize very quickly, I think a lot of people are familiar with the idea of you having zonal jets, and these acting as very strong barriers to transport. If you were to put two tracers in here, you get strong mixing and not much transport across these barriers. The same sort of idea holds if you just have topographically steered jets. So these jets passively steered by topography, tracers will get mixed. What's less clear is you have this dynamic interaction between the jets and topography. You've got jets merging, you've got jets splitting. Are there other ways for tracers to undergo large meridional excursions without actually crossing the jets? And these simulations that I've looked at show that these sort of possibilities are possible and are probably very relevant to what's happening in the ACC. And so these sort of mixing events, I think, need to be looked at further. The periodic sort of behavior that I showed on the last slide, similar sorts of things have been seen in the study by Hogg and Blundell, but in that case they were looking at much larger scales, and the changes were happening over the course of many years or decades. Whereas if you put Southern Ocean values in these sorts of simulations, even though they're a simplification, you get scales closer to a few months, which is really what you see in the Southern Ocean. And so the main conclusion really is there are a lot of difficulties here for parameterization. Transport properties vary non-monotonically on very small changes in topographical scale. You can undergo rapid regime shifts, and the possibility that the major transport events here are these different bursts that you see, and it's not a time mean average. Okay, thank you for your time.
Surely that cycle is a Charny-Devore cycle, isn't it? Charny-Devore multiple equilibria between topographic drag and something faster, which could be frictional drag.
Well, to a certain extent, I suppose that's right. I guess the key thing is looking at. What I was interested in is looking at how the Reynolds stresses kind of affect that. I mean, that's certainly true that it could be that cycle, I guess.
Yeah, I could be wrong. I'm wondering whether the topographic drag is pulsing in just the right way to organize that cycle.
I don't exactly know.
So you could do straight ridges, north-south ridges to check that point, couldn't you?
That's right.
But I mean, Charny-Devore is a resonance kind of thing, isn't it? I mean, I'm not sure.
Well, I mean, this would be a chaotic version of Charny-Devore.
That's a quick
But if you look at the time variation of the top panel shows some periodic behavior, not regime shift to right. So it's not a two preferable state. It's
No, it's more chaotic, but yeah.
I mean, I guess what I would argue with that is that I think what's most important in this cycle that you're seeing here is the mechanism in which baroclinic instability is extracting energy from the mean flow.
Mm-hmm.
And so what happens when this becomes very, very zonal is not so much that the friction is most important, but the baroclinic instability is actually quite inefficient at removing energy from the mean flow. And that's why you see this decay here, and that's why you get those bursts. I think it's less important as to what the kind of the frictional component coming out of here.
Can you clarify how you calculated the perimeter in your eddy diffusivity? So you calculate perimeters of contours or something?
That's right. So you calculate essentially so it's taken from the upper layer potential vorticity.
Right.
You calculate contour length.
That's clearly sensitive to resolution because that's going to go to infinity or it's going to grow up exponentially. If you really had an inviscid fluid, contour lengths are never going to be stopped from growing. So it's a definition which is sensitive to your demerits.
So you have to use a finite size measuring stick,
Right.
I think. Isn't,
I think,
There
well,
has to be a cutoff. to make
yeah,
it
that's
coarse
the
grained.
cutoff. Yeah. Is it the Nakamura thing?
that's correct.
And you repeat the question, no one will have heard it.
Oh, I'm sorry. So David wanted a definition of effective diffusivity. I guess his concern was that as you go to smaller and smaller resolution, those effective diffusivities, those contours become infinite. I mean, I think what's clear is that, again, so I should have mentioned that these effective diffusivities are not meant to be quantitatively compared to the sort of diffusivities you see in the Southern Ocean. I've really been using them to kind of get an estimate of kind of how the mixing changes in a domain sense, and that's why you look at the ratios to the flat bottom case. I guess my other argument would be that if you look at the eddy heat flux, it has the exact same sort of variability, and that's just another measure of what's being transported through the domain.
So quick question.
Yeah, I'm just going to check. In your simple model, you had did you have an infinite external radius of deformation, or you had a finite internal radius of deformation?
That's right.
So the external. Now, looking at in Peter's talk, just looking at the vertical structure of some of the eddies shown in the observations, clearly wasn't independent of height, and the amplitude did seem to decrease as you went down. I was wondering what the typical external radius of deformation is for these things, and how much potential energy there is in the elevation. The relative importance of the potential energy and the elevation you can see from the altimeter and the kinetic energy. Obviously, in your pictures, you can't see that because you've removed that. But have you any idea what it should be?
I don't off the top of my head. I could.
If that could have a role to play in the real system as well. I was wondering if it did.
I don't at this time, but definitely can talk about it.
So I have to cut it off